Maybe that still works. Hello. I hope everyone had a nice weekend. This is how you measure the size of a nucleus. We'll talk about that in just a few minutes. Kind of a really neat experiment, old but neat. First of all, speaking in neutrons live in the nucleus, and electrons surround them in a cloud. Again, protons and neutrons are in the nucleus. The nucleus is very, very tiny, and the electrons circle around the thing. They don't really circle around. There is simply a cloud, a region of space where the electrons are. We don't know where they are, blah, 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 but this is a region of space, and that is pretty much defined as the volume of an atom. We said that the thing that defines what an atom is the number of protons in the nucleus. That is the atomic number for an element, and it is on the periodic table. Periodic table is organized by atomic numbers. For carbon, it's 6. It has 6 protons in the nucleus. As we said before, it doesn't matter how many neutrons it has, how many electrons it has. If it has 6 protons, it's a carbon. We defined a couple things. The atomic symbol for an element. The atomic symbol is made up of the symbol from the periodic table and the mass number, which is the sum of the protons and the neutrons. We write the atomic number as a subscript in front and the mass number as a superscript in front. We did some examples of these. Again, we will see this on an exam. Make sure that you understand the notion. We said that if an atom had a family of atoms have the same number of protons, in this case these are all carbon, they can have different number of neutrons in the nucleus, so the mass number changes. For carbon, the 3 common isotopes are carbon 12, 13, and 14. Carbon 12 makes up about 98%, 99% of carbon around. The last 1% is carbon 13, and a teeny tiny trace of carbon 14. We arrange the electrons around carbon in 2 energy levels, and we're going to talk about those today. The inner electrons are the core electrons. They don't do anything, and we don't really care about them. The outer electrons are the valence electrons, and yes, they are important to us. Remember, the period on the periodic table reflects the quantum number for an atom. If we have carbon here in the second period, that means we have electrons from the first period, those are the core, and electrons from the second period, we'll call those the valence electrons. Now, carbon 14 is a radioactive isotope. It has a reasonable sort of half-life. It's made naturally in the upper atmosphere. There's always a steady state amount of it around. And living things tend to absorb carbon 14, both in food and CO2 and whatever. When you die, you stop absorbing, and by measuring the decay, you can figure out how old something is. You've probably heard of carbon-14 dating. Well, let's talk just a little bit about isotopes and radioactivity. Now, we're going to do an entire chapter on this, but this is just an introduction. The notion of radioactivity was discovered by accident back in 1896 in this lab somewhere in Europe. This guy was working on phosphorescence, trying to figure out why things glowed in the dark sometimes, blah, blah, blah. In the course of that, they used photographic plates. Now, photographic plates in those days are a whole lot different than we have today. They were a real bother to make. They really were. You had glass, then you had to put this layer of stuff down, put another layer of glass on it, all in pitch black, etc. So photographic plates were kind of precious to people. Turns out that in the lab, some guy, by accident, had a little jar of uranium salt and had no place to put it, so we just stuck it on top of the photographic plate and went about his business. Later on, it was developed, and he had ruined this photographic plate, which was a terrible thing, probably fired him. But what they noticed was the fogging where the stuff had been placed on the plate. This was the first notion of the concept of radioactivity. This was expanded by Marie Curie, among others, and she did lots and lots of work with radioactive isotopes. Eventually it killed her. What she basically was able to do was define the presence of radioactive particles. How did these things fog? Well, they fogged because they were emitting radioactive particles. This is supposed to be a nucleus. There are two ways the nucleus can expel things. There are actually many, many more. We'll talk about those in the later chapter. But the two simple ways. If your nucleus is unstable, it can actually expel a chunk with 2 protons and 2 neutrons. Now that's a helium nucleus. It's called an alpha particle. And basically it's just an unstable nucleus expelling a chunk. It can also expel a beta particle. A beta particle is much higher energy, and it's an electron. Now, you might ask yourself, what's an electron doing in the nucleus? Right? Well, you could. Turns out it's interesting. The electron actually comes from a neutron. The neutron breaks down, forms an electron, which is negative, and a proton, which is positive. Proton stays behind, the electron whizzes out. The electron, of course, is -1. This has 2 protons, 2 neutrons. It has no electrons, so it's a +2. Any questions? There's also a third particle called a gamma particle or gamma ray. Gamma rays are basically a photon, so that's just like light, except very, very, very high energy. Gamma rays can travel clean across the known universe, and we can detect them just like that. Alpha particles are big, they're +2, they're not very energetic. If the alpha particle is heading somewhere and you put a piece of paper in the way, it'll stop it. Beta particles, much more energy, it would take maybe a centimeter of lead to stop it, or a standard sort of beta. Gamma particles can go right through 10 centimeters of lead. They could probably go straight through the Earth, and like I say, from very, very far away. Very high energy. Turns out the most toxic of them all, believe it or not, is the alpha particle. Alpha particle, even though it is such low energy, if you ingest it or inhale it, it will sit there in your lungs and will very slowly deposit these alpha particles against all the cells that are in your lung. This is a really bad thing, and you die. Plutonium is a very common alpha emitter. About a microgram, that's 10 to the minus 6 grams, is enough to kill you. Polonium is much, much worse. It's 1,000 times more toxic. I think polonium is what killed Cody, I think. But we can detect radioactivity using a Geiger counter. A Geiger counter is really kind of simple. You can't use a Geiger counter to measure alpha particles because they're so low energy they can't get in. But a beta or a gamma, what we have here is a tube that is partial vacuum. There's a little bit of a gas added on purpose. Has a window and basically has an electrode down the middle. You charge one side positive, charge this electrode in the middle negative, and when a particle comes in, it's called ionizing radiation, okay, because it has lots of energy. If it happens to hit an atom, it will ionize it, so make it positive or negative. That then allows a spark to jump from here to here, and you get the standard collector. If we have a nucleus that undergoes spontaneous decomposition to do something, generally we refer to that as a radioactive substance. Well, that's just the definition. Any questions? Let's look at alpha particles a little more closely. Alpha particle consists of 2 protons, 2 neutrons, helium nucleus, mass of 4, a charge of +2. An example of something that emits an alpha particle is uranium-238. This is plain old standard uranium you can dig out of a rock. It's the most common form. Uranium-238 has an unstable nucleus, and it can lose 2 protons and 2 neutrons. When it does, this is our alpha particle right here, it will change to a different element. Why does it do that? Because the atomic number is changing. We're losing 2 protons, so we go from 92 to 90, and we just made thorium. We also lose 2 neutrons, so the mass goes from 238 down to 234. Any questions? Most people will write this alpha particle this way. You will sometimes see it with the Greek letter alpha instead. Same thing. Any questions? Oh, yeah, let's do our math here. This is what's called a nuclear equation. Just like a chemical equation, things must add up on both sides. Okay? Things must add up. In this case, we're talking the numbers of protons. Here we have 92 protons on this side we must have a total of 92 protons on this side, 90 in our thorium and 2 in the helium nucleus. Likewise, our mass number here is 238. The mass numbers on this side must also equal 238 when you add them up. 4 for the alpha particle, 234 for thorium. We will revisit this again in much more detail when we do the chapter on radioactivity. Okay, this is redundant. This is 92 and this is 238. Maybe that slides in there twice. As we've seen, we can take one atom and through radioactive decay, we can form a new one element to a different element. We can do this transmutation lots of different ways. One of the most dramatic ways is neutron capture. So imagine that you have a nucleus that's more or less happy, and somehow a neutron comes by, hits it, and sticks. Odds are, when that happens, this nucleus is no longer happy, that it reaches a point of instability. When it becomes unstable, it will do something. It can release particles. In fact, it can even split into smaller atoms. Uranium-235, this is the fissile version of uranium. It's what you use to make bombs. Can capture a neutron. When it does, the neutron will stick just for a nanosecond. The nucleus becomes very unstable and splits in half. Not quite half, but splits. When it does, it releases a huge amount of energy. This is the concept of nuclear fission. Let's watch it happen. Here comes our neutron. Now you'll note the neutron has no protons, so its atomic number down here is 0. But it has a mass number of 1 because it has 1 neutron, doesn't it? So here it comes. Sailing in, lands, and kaboom, it opens up. Now, lots of energy is released, like I said. Also, 3 neutrons are released. These are high energy neutrons because they were just blown out of this nucleus. What we've done in this case is we formed krypton, 36, mass number of 91, barium, 56, mass number of 142, and we have 3 neutrons. Again, these are high energy neutrons. If you add up all of these guys here, you will get 236. If you add these guys, you will get 92. It's a valid equation. 235 plus 1, 91, 142, and 3. Again, these add up to 92. Because we have these neutrons that are released when this fission occurs, if there happens to be another uranium sitting close, there's a good chance that one of these neutrons is going to land in its nucleus. And that's going to split. And it's going to release 3 more. Going to hit another one. Going to split. Release 3 more, etc., etc. This is what's known as a nuclear chain reaction. This is a little movie that's designed to mimic that. It's a very classic thing. You can't see it yet, but it's a box with mouse traps and ping pong balls. And you put a ping pong ball on top of every mouse trap. Then you start it off by dropping in another ping pong ball, that's our neutron. It hits, one bounces out, hits everything, and whoosh, they're all gone. That's the way nuclear fission works. Here's our box, and whoosh, they're all gone. Very rapid. Again, this process takes nanoseconds to occur in a critical mass of, say, uranium. When this happens in uranium, the energy that's released is what makes a fission bomb. Now, just for an exciting preview, when we do our chapter on radioactivity, we'll actually talk about how to make one of these. And if you add the stuff, it's actually dreadfully easy. That's why it's so scary. Any questions? Well, we just took a neutron and we stuck it in a nucleus. This is not really easy, typically, because a nucleus, as we've said many times before, is very, very small. Very small. A gentleman by the name of Rutherford designed a set of experiments to measure just how small it was. What he did was he took an alpha particle source, so, you know, a lump of uranium, passed it through little tiny pinhole, and then he took gold. Remember we said gold was the most malleable of all metals. You can pound it out so it's an atom or two thick. It's amazing. So he did this, took this little tiny piece of gold leaf and put it in this beam of alpha particles. What happens is the alpha particles will approach the gold nucleus. Now, this is positive, and so is the alpha particle. As it approaches, it is deflected. And it is deflected up and away from the nucleus. See all these little spots here? That's photographic plate. So you can actually see where the stream of alpha particles hit something and the angles that they were deflected. From fairly simple calculations, you can actually then measure the size of that nucleus. Turns out that the nucleus in a gold atom was about 10 to the minus 50 meters. Okay, that's tiny. The whole thing with the electrons on it is about 10 to the 10th. If you do the calculation, 0.0004% of the volume is the nucleus. And yet that's where all the mass is. So it's amazing that we can manage to stick a neutron in a nucleus, but obviously it happens, and obviously we get fission. Any questions? All right, we will return to this topic later. We'll do an entire chapter on it, like I said. Let's now look at the electrons. Enough about the neutrons. I said that carbon has electrons in two energy levels. When we talked about our periodic table, we said that the period, that's the vertical grid here, represented the quantum energy level. Since carbon is in the second period, the first period are these guys in the middle, and the second period are on the outside. The core electrons don't do anything, they just kind of live there. Have to be there, but we don't care about them. The valence electrons, we'll see, this is what makes bonds, and this is very important. The quantum level, also known as the period, defines the number of electrons that can live in an atom on the various periods. There's a simple equation for this. It's 2n squared electrons, where n is our period number. So if n is 1, 1 squared is still 1. Multiply it by 2, we get 2 electrons in our first quantum level. Turns out we have 2 atoms in our first quantum level, don't we? Hydrogen and helium. Our second quantum level, if n is 2, 2 times 2 is 4, 4 times 2 is 8. We can have 8 electrons in our second level. We can have 18 electrons in our third, 32, 50, and on and on and on. Now, within each quantum level, electrons exist as sets of either 1 or 2. They live in what are called orbitals. Orbitals are just regions of space where this electron lives. The simplest orbital is an s orbital. Again, every orbital we'll see can only hold 2 electrons, no more. This is a sphere, basically, spherical symmetry. It's an s orbital, and again, 2 electrons. The next set are p's. There are 3 p electrons, or 3 p orbitals. We call them px, py, pz, and each of these can hold 2 electrons. Now, you look at the geometry here, it's very tempting in your head to say, oh, 1 electron's there, 1's there, right? No, no, you don't know that. All you know is that within that region of space there are 2 electrons. And interestingly, see this little spot in the middle? Called a node. The electron is never at the node. It'll be on both sides, but never in the middle. The next set of orbitals are d's. There are 5 d's. As you see, they get really interesting. This is one of my favorites. You know, lobes with a little inner tube around the middle. Once again, each of these can only hold 2 electrons. So in our d orbital, we can hold 2, 4, 6, 8, 10 total. F's are even more interesting. There are 7 of these guys, and they have very interesting geometries. In this course, we're going to stick to S and P. Pretty simple. Any questions? All right. Well, let's talk about these guys and the periodic table. You've probably wondered why it's particularly shaped like this, with this big hole in the middle and these guys on the ends and stuff like that. That's because this is our first quantum level. It's an s orbital, and we can put in 2 electrons. If we have 1 electron, it's a hydrogen. If we have 2 electrons, it's a helium. Our second quantum level. First thing we're going to have in these 2 is an s orbital. Remember, the s orbital can hold 2 electrons. So we put 2 in there, 1, 2. We call this the 2s. For the rest of these, we bring in p orbitals. These guys are our sets of 3 p orbitals. 2 electrons, 2 electrons, 2, a total of 6. We have 1, 2, 3, 4, 5, 6 atoms. We're just adding electrons along with the protons to make the atoms. Our third, we're still doing 3s now. So first 2 electrons go in the s. We can hold a total of 18, but the next ones that fill are actually the 3 p's. So 2, 4, 6, and 2 more here, that's a total of 8. These guys don't fill until these fill first, and when they do, we get 4s, 3d, and finally 4p. We're not going to talk about those. Again, just periods 1, 2, and 3. But that's why it looks the way it does. Any questions? There's one other thing that we have to know about the electrons as they live in these orbitals. Quantum mechanics gives an electron a quantum number that is called spin. Now, you can imagine that the electron is spinning. It's really not, but you can imagine that. And if an electron was spinning, it would generate a magnetic field. You can therefore have electrons spin 2 directions, one generating this field and one generating the opposite. The rule is that electrons in an orbital must have opposite spins. So plus 1/2, minus 1/2 is the spin. So as we're putting the 2 in an s orbital, one's up and one's down. All right. HUND'S rule, just as a slight take on that, what HUND'S rule says is that when you're filling orbitals that have, say our p's, we're going to put 1 electron in every orbital and then pair them up. So they go in one at a time, and then we pair. We'll see an example in a minute. Hydrogen, we have 1 electron in the 1s orbital. One way we show it is this way. Here's our 1s, and I'm going to use little arrows to indicate the spin. So we have an arrow that's up. That's 1 electron in the 1s orbital. Helium, again, we're at the 1s orbital. We have 2 electrons. One will be up and one will be down. The shorthand way to show this, and the way you will show this on an exam, is this way. 1s1, 1s2. And everybody just understands that when you have 2, 1 is up, 1 is down. Let's do a quick problem. Carbon. Carbon's our friend. It's in the second period. Atomic number is 6. Let's think about its electron configuration. Here's our periodic table. Carbon is right here, number 6. So, when we think about the electron configuration, what you want to remember is that everything that's north of it and this side of it is going to be filled. is going to be filled. So in order to get to our second period, we had to fill the first. Then we start on the second period. We fill the two S's here, and then we put electrons in the P's. So let's look at it. 6 electrons. The first quantum level is filled. The second will have 2 S electrons and 2 P's. There's our 1s. It's full. It's the core electrons. They just sit there. Our 2s is also full. Again, that's those 2 electrons right there. Now we have 3 p orbitals, don't we? But remember, the electrons have to go in one at a time into the orbitals. Then you pair them. Therefore, in our p orbitals, we have 1, 2 electrons. Now, on an exam, you're not going to draw little arrows and stuff like that. You will use the shorthand method to represent this. Here's our total configuration, 1s2, 2s2, 2p, 2. And this is how you write it. Everyone is supposed to understand that when we have 2p2, it actually means 1 electron in this orbital, 1 electron in this one, for a total of 2p. Let's do another one. Fluorine. Fluorine is also in our second period. It lives right over here. So just like carbon, the first period is going to be filled. The 2s is going to be filled. And then we're going to have 1, 2, 3, 4, 5 electrons in the P's. One S is full, 2s is full, 5 electrons in the p orbitals. All right, let's do it. There's the 1s. 4 electrons, it's full. Here's the 2s. First 2 columns there, it's full. We have 3 p orbitals, and we have 5 electrons. HUND'S tells us these go in one at a time. We have 2 more electrons left over, don't we? Now we start to pair them with opposite spins. And that is fluorine. On the exam, again, you don't have to draw little arrows. You just simply would write 1s2, 2s2, 2p, 1, 2, 3, 4, 5. Any questions? This is the periodic table. And this is just a really neat little thing, I think, because it explains the periodic table nicely in terms of orbitals. The first period, 1s, right here. Second period, we fill the 2s and the 2p's. 3s, 3p's, 4s, 3d, 4p, etc., etc., etc. You see down here, with the inner transition elements, is where we get to the F orbitals. Very complicated. So, what's this look like on an exam? Sulfur. Which of these is sulfur? Well, you gotta find sulfur on the table, don't you? Sulfur. lives in the third period. Oh my goodness. And it's right there. Now, what does that mean? That means that the first period is completely full. So 1s is going to have 2 electrons. Well, A, B, C, and D are all correct. Secondly, if this is in the third period, that means that the second period is full also. So we have 2 electrons in the 2s. A, B, C, D, yeah, they're all good. Third thing, the 2p is completely full. It can hold 6 electrons. So that's 2p6. Oh my gosh, 1, 2, 3, 4. So all of these are the same. Our third period. In order to get over here to sulfur, we have to fill the 3s, don't we? So that's a 3s, 2. Oh, by George, they're all the same. How many electrons are in the 3 p orbitals? This is the p block. 1, 2, 3, 4. 3p4. That's it. How many s electrons in beryllium total? Well, beryllium is here. How many s electrons are there? Well, it's in the second period, so that means the first one is full. That's 2s electrons, right? It's over here. In the 2s, we have 1, 2, total of 4 electrons. See, that's simple. Lithium. Oh, this was a trick question. I was so embarrassed. Because people miss it. You know, when you write exams, sometimes you put questions on there that are just designed to be simple so that everybody's going to get it and it makes them feel good, right? That was supposed to be this. And almost everybody missed it. Lithium has atomic number of 3 right here. The number of electrons in the first shell is what? Oh, it's at the second quantum level. So the first shell is full, right? How many can you put in there? 2. Everybody put 3. Number of pairs of electrons in the p orbitals with the electron configurations of 1s2, 2s2, 2p4. So we're talking about these 4p electrons, right? We have 3 orbitals. We put 1 electron in each orbital first. Boom, boom, boom. We have 1 extra electron, so then we start pairing. How many pairs in here? Just 1. This pair right here. I think there's 1 more here. Number of s electrons at the highest energy level of neon. Neon is here. Okay? Number of s electrons in the highest energy. Highest energy in this case would be the second period, right? How many s electrons can we put in the second period? Just 2. All right, this takes a little bit of practice to do, and so we have a tutorial. We just did sulfur. Let's do sulfur again and see how we enter it into the tutorial. This is basically a table, and you will put a 1 or a 2 in a cell, and that's it. You don't put zeros, you don't put 6, you put 1 or 2. Okay, sulfur. Sulfur, we know, lives over here. It's in the 3rd period. So that means that the 1s, that's this guy, is full. We have 2 electrons in the 1s. We're in the 3rd period, so the 2nd period is full too. We have 2 electrons in the 2s. We have 6 electrons in the 2p's, but remember they're paired up 2, 2, and 2. Finally, the 3rd period. Here we are. 2 electrons in the 3s. Now, we have a total of 1, 2, 3, 4 electrons to deal with, right? We're going to put them in one at a time first. And now we have 1 extra electron, so we'll pair this guy up and make it a 2. And we got it right. Lithium, how easy can you get? Lithium, once again, lives right here. It's in the 2nd period, so that means the first one is full. 2 electrons. It has 1 in the 2s, and that's it. No zeros, no nothing, just a 2 and a 1. Do one more, silicon. Silicon is right under carbon. It's here in our 3rd period. We know what to do, right? If it's in the 3rd period, the 1st period is full with 2 electrons. The 2nd period has 2 in the s, 6 in the p. So a 2. And then 2, 2, 2. 3s is going to be full. And now we have 2p electrons, and we put them in one at a time. Boom, boom. Five points. Any questions?
How do you know that you did all these? Is it on your grade book? Because I have no grades in my grade book yet.
Oh, I haven't put them in yet.
Okay, even the chemistry, the lab.
This is Blackboard, right?
Yeah, even the lab, there's no.
I haven't put it in yet. Sorry.
Okay.
But I will. I
Okay.
will. And when you take the quiz, the good thing about taking the quiz is that it will post it automatically. So you don't have to wait for me to grade it. All right. So now we can understand a little bit better what's going on with carbon. This is our s orbital, or 1s. There's our 2nd quantum level, that's these guys, a total of 4 electrons. Okay, we said that these were called valence electrons. These are core, and these are valence. Valence electrons are what form bonds. They're the highest energy electrons in an atom, and they're the ones that are going to make the bonds. Now, today we kind of understand chemical bonding on lots of levels. That wasn't always the case. It was, gee, for many, many years people did nothing but argue about how to make bonds and stuff like that. This was all helped a lot by a guy named Lewis. Lewis came up with Lewis dot structures. It's a fairly simple concept, just with one or two rules. What you do is you start off just with the symbol of the element. So, just from the periodic table. And then you place the valence electrons around it. We will use those valence electrons combined with others to make bonds. So, let's look at carbon. Again, carbon, our symbol is C. Carbon has, in the second period, 2 s electrons and 2 p electrons. Those are going to be our valence electrons. So what Lewis had to do was to take our symbol for carbon and put little dots around it. Now the convention is to do north, south, east, west. I will do that. There is one rule. The rule says you put them all in as individual dots until you get to 4. Then you start to pair them up. Okay, carbon, 4 dots. Let's look at fluorine. Fluorine is an F right here. There's our symbol. It's going to have 1, 2, 3, 4, 5, 6, 7 valence electrons. We put these in one at a time. Then we start to pair them. This is fluorine with its 7 valence electrons. Now, does it matter if this guy has a partner or if this one's single or that one? No. This is bookkeeping. It doesn't matter where you put the unpaired electrons. Only thing that's important is when you draw the Lewis structure for the fluorine atom, you have 3 sets of paired electrons and 1 unpaired electron. The only thing that matters. All right. How do you know how many valence electrons? Well, remember, a long time ago I said, yes, there are in fact 18 things going across our periodic table. But we're only going to do 8 of them. The representative elements. Why? Because the group number corresponds to the number of valence electrons. 1, 2, 3, 4, 5, 6, 7, and 8. That's the very simple way. You look at your periodic table. We just did fluorine. Fluorine is in group 7. It will have 7 valence electrons. Now in this end. All right. There are many things you can do with Lewis structures, and we will. One thing you can do is to show the structure of a charged atom. This is called an ion, I-O-N. And we have 2 types. If it's positive, it's called a cation. If it's negative, it's called an anion. So, how do you show this in a Lewis structure? You start off with the basic structure of the atom, and then you add or subtract electrons. Chloride. Chlorine is right here, third period. It's in group 7. So it has 7 valence electrons. We write the Cl. Now we're going to put 7 electrons around it, 3 pairs, and 1 by itself. Again, it doesn't matter where the lone electron is. Doesn't matter. This is neutral chlorine. Now, to make the chloride anion, what we need is 1 extra electron because it's negative. That means it has 1 too many electrons. So to draw it, we simply stick in another electron and show we have a negative charge. Now, an interesting thing has happened here. This is no longer the electron configuration of chlorine, is it? It has 8 valence electrons. That means it's equivalent to argon. Argon, the inert gas. We'll come back to this point. Let's do sulfide dianion. By this time, we know where sulfur is. Right here. It's an S. It is in our 5th group, right? So it will have 5 valence electrons. Draw yourself an S and put 5 little dots around it. Six dots. I'm sorry. I'm too close to the thing here. I can't quite see very well, can I? It's in group 6, not 5. So it has 6 valence electrons. 2, 4, and 2 singles. Right? Now, to make the,
So the number of dots is just the number of the
it's the group number, right?
You don't have to put it in that order. You could
Nope.
just put it.
Any way you want. Now to make the dianion, we just need 2 more electrons. We'll pair them up and show this is now -2. Do nitride. First of all, find nitrogen. Right here. This one's in group 5, right? So draw yourself an N and put 5 electrons around it. With 5 electrons, we'll have 1 set that's paired and 3 individuals. Now the nitride anion is at -3, right? So we need 3 more electrons. And that's the nitride anion. One more. Let's be positive here. Sodium forms a cation with a +1 charge. That means it's missing 1 electron. So sodium lives here in the first group. Symbol is Na. Because it's in the first group, it will have one valence electron. Now, how do we make this a cation? How do we make it positive? We simply take its electron away. And that's the sodium cation. All right, there's been a trend here. I kind of let on a little bit earlier, but let's go back and think about it. What we're trying to do here, as we made these ions, was we filled up the valence shell. Filled it up. For example, chlorine, here in group 7, we added one electron, and that made it the equivalent of argon, the inert gas. Why is it inert? Because all of these have complete shells. Except for helium that can only have 2, these guys all have 8. They don't have unpaired electrons. They can't make bonds. For sulfur, we added 2 electrons. Started here. Again, we wound up the electronic configuration of argon. How about sodium? Started here. Took its electron away. We are now going up to the second period. We have the configuration of neon. This is called the octet rule. As we go and make bonds and stuff like that, what we're trying to do is to make a full valence shell, full with 8 electrons, 2 for helium or hydrogen, but a full valence shell, because that makes it equivalent to an inert gas, and the reactivity stops. The octet rule. Now, we used Lewis structures to make ionic or ions, right? I told you a long time ago that there were 2 types of bonding. One was going to be ionic. It would involve ions, like we just made. The other was going to be covalent, or shared. Turns out that chlorine, Cl2, is an example of a compound that has covalent bonds sharing electrons between them. So how do we do this in a Lewis structure? Well, this is chlorine. Chlorine is over here in group 7, right? 7 electrons. All in the world we have to do to make Cl2 is to bring another chlorine in, and there we go. The electrons that are unpaired pair up. Let's undo that if we can. There it comes. They pair up. Now, if you look at the electrons around this chlorine, how many do we have? 2, 4, 6, 8. This chlorine, 2, 4, 6, 8. We count the shared electrons for both atoms. Both of these have an octet. That is why Cl2 exists. When you draw it out, chemists get really tired of drawing little dots. Instead, we're going to use a dash. Whenever you see a dash like this connecting two atoms, you stop and you think to yourself, that dash means we have two electrons in that bond, and it's a covalent bond where they're sharing electrons. This is how we build molecules. Let's build one. How about ammonia, NH3? The way we build is we find our guys on the periodic table, figure out how many valence electrons they have, pair them up so that we have 8 if it's in the second period and below, or 2 if it's hydrogen. So we start off by drawing our atoms and their dots. Nitrogen is group 5. It will have 2 electrons paired and 3 single electrons. Hydrogen is in group 1. It will have 1 unpaired electron. And this is what we got. 3 hydrogens, 1 nitrogen. The nitrogen has 1, 2, 3, 4, 5. Each hydrogen has 1. Step 2, we're going to scooch these up and let them get friendly. And so we have this. Now, how many electrons are around our nitrogen? 2, 4, 6, 8. It has an octet. How many electrons around the hydrogens? 2. This has 2. This has 2. This is ammonia. Now, if we drew it out with our line bonds, we would do this. And again, we refer to these as single bonds. Any questions? Let's do one that's more fun. Nitrogen. Nitrogen is in 2. 2 nitrogens stuck together. Going to do this the same way. Nitrogen is here in our 5th group. So we have 1 nitrogen with 1, 2, 3, 4, 5. Another nitrogen with 1, 2, 3, 4, 5. What we have to do is pair these guys up in such a way that each nitrogen has an octet. Think about how you're going to do that. Well, I hope that this works on my computer without crashing anything. Come on, there it goes. Come on. All right, here's my 2 nitrogens, and they each have 5 dots. Oh, you can't see that, can you? Sorry. Okay, we'll go back to here, and I'll do this the old-fashioned way, if I can find something to write with. And there is nothing to write with. Oh my goodness.
Yeah, I got some.
Well, here's something. All right, well, it's orange. Oh, you just happen to have something. Okay. Okay, let me have just a black. And you have a red? Oh, sorry. Oh, that's great. Thank you. All right, so here we go. We have our two nitrogens, right? We put 5 electrons around each one. Okay, now, if we put these together, right, obviously, we can make a bond between those guys, right? That's simple. We can do that. But that would give us 1, 2, 3, 4, 5, 6 electrons around the nitrogen. 6 is nice, but it's not 8. So what I'm going to do is take one of these guys and just move it in like this. Take this guy, move it in like this. And now we've got this. How many electrons around each nitrogen now? 1, 2, 3, 4, 5, 6, 7. 7 is better than 6, but it's not 8, is it? So let's do that same operation again. Move that up, move that guy up. Now what do we have? 1, 2, 3, 4, 5, 6, 7, 8 around this guy. 1, 2, 3, 4, 5, 6, 7, 8 around this guy. Eight electrons around this nitrogen, 8 electrons around this nitrogen. Now, first thing you could say to yourself is, what gives you the right to do that? Remember, I said Lewis structures are just bookkeeping, right? For bookkeeping. We can put them anywhere we want. This is what we call a triple bond. 3 bonds between these 2 nitrogens. The bond between nitrogens, because it's 3 separate covalent bonds, is very, very strong. Nitrogen is very essential for fertilizer and stuff like that, right? Converting atmospheric nitrogen to fertilizer is really tough because this bond is so incredibly strong. Any questions? All right. Well, let's go ahead and move on then to types of compounds. We've seen examples here where we make ions. We've seen this before. This is methane. Molecular compounds, elements share electrons. These represent shared bonds, so shared electrons to each, and they form covalent bonds. When you make a compound out of ionic material, what you're going to do is basically take cations and anions and put them together. How do they go together? They go together electrostatically because the plus attracts the minus, etc., etc. What does the array actually look like? What determines that? It's the size of the atoms and how they pack together most efficiently. This is an ionic compound. Chloride anion, sodium cation. Simple electrostatic attraction. Any question? All right. We have two types of compounds, right? We can make covalent bonds. We call that a molecular compound. That's a molecule. We can also have an ionic compound, where we simply have ions that are stuck together electrostatic. How do you know what kind of a compound you're going to make just based on the atoms that are in it? Turns out it's simple and goes back to our periodic table. Remember, in chapter 2, we said that in this colored periodic table, that all of these purplish blue guys were metals, right? We said over on this side, these yellow guys were nonmetals. And in between, and so is hydrogen, and in between, we have this little array, and we call those semimetals. So what type of a compound will you make from a given set of elements? It's actually very, very simple. If the compound contains only nonmetals or semimetals, so the yellow and the green, it will be molecular. Nonmetals, semimetals, molecular. If it has a metal anywhere in it, it will be ionic. So all you have to do is look at your elements. If one of them is a metal, forget it. It's an ionic compound. If there is no metal, only nonmetals, semimetals, it will be molecular. Magnesium chloride. What's that? First thing we do is find magnesium. Magnesium is here, isn't it? It's a metal. It's one. Chlorine is over here. It's a nonmetal. If your compound contains a metal at all, it is ionic. It is not molecular. Hydrogen fluoride. Hydrogen is on this side of the periodic table, but remember, the periodic table you get for your exam is not colored. Looks like this one. So just have to remember this is a nonmetal. Fluorine is over here. It's yellow. It's a nonmetal. This is a molecular compound with covalent bond. Silicon tetrachloride. Silicon is right here. It's a semi-metal. Fluorine's a non-metal. It is molecular. Sodium bromide, well, that's a no-brainer. We've seen sodium so many times. It's right over here in group 1. It's a metal. Bromine is a non-metal. This is ionic. And finally, remember I said that chlorine forms CO2, right? We understand why and how now. Bromine does, Br2, etc. Sometimes elements are just happiest if they're stuck together. Sulfur is one of those. What are the bonds in S8? Well, sulfur is right here. It's a non-metal. Therefore, this is a molecular compound. Looks like a crown, kind of cute. All right, what about test questions? Here we want to simply indicate if they're molecular or if they're ionic. Very quickly, we'll run through the list. Nickel chloride. Where's nickel? Right there. It's a transition metal. It's ionic. Dihydrogen sulfide. Hydrogen's yellow. Sulfur's yellow. Molecular compound. Dihydrogen sulfide is typically called hydrogen sulfide, and this is the smell from bad well water. Silicon, tetrahydride. Silicon, right there, it's green. Hydrogen is yellow, molecular compound. Sulfur trioxide. Oops, is molecular. Sulfur is there, oxygen is there, 2 nonmetals, molecular. Calcium hydride. Iron calcium is here in group 2, isn't it? Hydrogen is there, ionic. One more set here. What's CS? CS is down here, underneath sodium, lithium, potassium, rubidium, cesium. Cesium is a metal, very, very explosively reactive with water. But it's a metal. Therefore, it's ionic. Diiodine heptaoxide. Iodine is here. Oxygen is here. This is a molecular compound. Now I know all of you are thinking to yourself, my goodness, how does he know what to name all these things, right? You're probably envious. In our next chapter, we will learn how to name all these things. Isn't that exciting? Oxygen difluoride. Oxygen, right there, fluorine right next door, a molecular compound. Carbon tetrahydride, that's methane. Carbon is a nonmetal, hydrogen is a nonmetal molecular. And finally, again, the drop dead simple stupid sodium chloride, sodium, chlorine, oops, there it is, ionic compound. All right, the next chapter we will talk more about bonding. We will talk more about the octet rule.